Good morning, Jean-François, Chrysalide Engineering, working on this PLC project. And last time we checked the buck power supply, which converts from 24 volts to 6 volts, or actually between 8 and 30 volts. We have the buck stage, and behind we have a regulator stage, and we have a filter to provide the analog VRF, and we have the protection back supply diode, and a couple other features. So we are going to continue study this project. And while we're doing this, why not use the line LED power available over voltage like this, above 30 volts, and power LED. And I meant fuse fail power LED and fuse fail diode, so that if we have a power in and we don't have any power output to the ground and through this line to VF voltage, we will light up this LED. So we have a fuse blown LED, isn't it? We have a power another voltage in case something happens and we start to run close from 30 some volts. And we want actually to lower this over voltage a little bit. So we want to check the datasheet of this component. The Zener voltage of this is 28 to 32 volts. So we perhaps want to have a little bit of margin, and we probably want to have a typical Zener of 27 volts. 27 volts should be good. So we need to tweak that, because then the problem is if we have on the low side around 25 volts, we are too close from nominal voltage 24 volts, and there are risks that this unit will run with this LED always on. So we will keep this one. 30 volt nominal, 28, 32, and update the protection diode. This protection diode needs to be one step higher. We will need to get through 33 volt nominal, which means 38 volts conducting, and we have 53 volts set 7.5 amps. So it's higher than the so we can keep actually this one. So say from 30 volts we start to eliminate 33 volts to protect up to 48 volts. And if we see the curve, it seems to be linear. So if we roughly calculate our 3 amp 1.56 volts per amp on this diode, then we have roughly speaking 2 volts at 3 amps, and we will blow the fuse from 36 volts. So from 36 volts we will blow the fuse, and 36 volts we are already showing another voltage, so that should be fine. So essentially this circuit between 30 and 36 volts, it will provide the voltage LED, and roughly speaking between 35 to 38 volts in this region, we should start to blow the fuse over some time, depending on temperature, depending on parameters. So that's the purpose of this circuit. Should work well with this configuration. That's essentially the Arduino circuit. It's a mix of an Arduino circuit, because this is the R4 slightly modified. The microcontroller is on the bottom right over here, the programming port, and we had some I2C and communication port. I jump over here to turn on the pull up for a serial line. And we have power conversion over here in the middle, and conversion for the inputs over here, left and right. We have the static fuse over here, power LEDs here, terminals, input, output, and the relays. That's the board layout, work in progress, with actually clocks, because it misses the 32K and 16 meg crystals, so the Arduino should be working good. And there are some limits of temperature, so then it should start to have some issues, and I don't want to have USB issues at different temperatures. So the reason for putting the crystal back in Arduino, there's only the provision, and apparently with the R4 they decided it's not necessary. So we have our terminals over here top left, the port here and there, power conversion here, the digital inputs over here, digital outputs, and the relay control. And we have analog inputs conversion over here as current or voltage input. the RS485, which is our serial input-output, and the Arduino microcontroller in the middle, but it's actually according to the R4 version, which is a much simplified diagram, so the reason for this. We can dive into these input-output blocks later on, so thanks for your interest. You can follow this project if you're interested in the implementation. Thanks.